Welcome back. We will be now looking at limits at infinity. Um, so, so let me start with a couple of examples here. So if I look at the limit as x goes to infinity of 1 over x squared, then that limit would be 0. So what do I mean by this limit? Well, this is what I mean by this. So we are asking, as x gets bigger and bigger in the positive direction, what is happening to this function? And so you can see that what is happening here is that the numerator is 1, but the denominator is getting bigger and bigger. So it's getting larger and larger. So this fraction then it gets smaller and smaller. In other words, I can make the value of this fraction as close to 0 as I like simply by choosing x large enough. So for example, if I want this fraction to be less than, let's say, 0.0001, all I have to do is I have to pick x, say something like x to the 10 to the power 2. So if I pick x to be 10 to the power 2, then obviously then this fraction would be less than 0.0001. So I can make this fraction as small and close to 0 as I desire simply by choosing x big enough. Similarly, if I look at the limit of 1 over x squared as x goes to negative infinity, I also get 0. The reason is, so in this case, x is becoming large in the negative direction. However, it is very large, so we are still dividing 1 by larger and larger positive numbers, so we would be getting 0. So imagine that x is something like, x is something like 10 to the power 10. If x is 10 to the power 10, then this guy would be x to the power 20, and 1 over x to the 20 would be, it would be a number like 0.00001 with 20 zeros. So this limit would also, so here we are saying as x gets bigger and bigger in the negative direction, or if as x decreases without bound, what is happening to this fraction? Now here, instead of 2, I'm just putting in a 2 here, and the limit would still be 0 for the same reason. And even if I put in a negative 2, the limit will still be 0 because we are still dividing negative 2 by larger and larger denominators. Now, if I look at the limit of 4x cubed as x goes to infinity, so here we are saying x is becoming large, right? So if x becomes large, then x cubed is becoming large. So then the limit would be infinity. So 4x cubed will become large without bound. If x is becoming large in the negative direction, then so when x is large and negative, x cubed is also large and negative. So you see that as x decreases without bound, 4x cubed also decreases without bound. That is, I can make this guy as big and negative as I like by choosing x suitably large and negative. So this limit should be this limit we're going to say this is negative infinity. The limit as x goes to negative infinity is of negative 3x to the 4. So here you have to be a little bit careful, because when x is negative large, x to the 4, because of the even power, x to the 4 is positive large. So when x is negative large, x to the 4 is positive large, multiplied by negative 3 would be negative large. So we see that this limit is negative infinity because this function decreases without bound as x decreases without bound. So generally, if p is a positive real number and k is any real non-zero number, then we can say we can say that the limit of 1 over x to the p as x goes to negative infinity is 0, because as when x is large and negative, x to the p will also be large, whether negative or positive depends on what p is. But in either case, we would be getting 0. And also the limit as x goes to positive infinity of 1 over x to the p would be 0 as well, again because the denominator goes to infinity as x goes to infinity. The limit of k times x to the p, well, the limit of that as x goes to negative infinity or positive infinity will be either infinity or negative infinity, depending on what k is and depending on what p is. But one thing for sure, if p is a positive power here, if p is a positive real number here, and k is a non-zero real number, then the limit here would be either these two limits would be either infinity or negative infinity. Now, I do need to provide a condition here because when p is half, then we are talking about even roots. In that case, this limit doesn't make sense because when x is negative, even root of negative numbers is not real. So this limit here only makes sense for us when p is not an even root. So we need x to the p to be a real number for negative values of x for this limit here. There is no point in memorizing this 4 limits. Like I said, as we did in the previous slide, we can just analyze case by case like this. But if you want to memorize them, that's fine too. So if I have a polynomial function, what is the limit of the polynomial function at infinity? So if I have a polynomial function of degree n where the leading term is an x to the n, then it turns out that the limit of p of x is the same as the limit of just the leading term, and it could be, and that limit is, so if I take the limit of the I should take it back. If I'm taking the limit of the polynomial at infinity or at negative infinity, then the limit would be the same as the limit of the leading term, which could be either infinity or negative infinity. So let me say that again. If we are taking the limit of a polynomial at infinity or at negative infinity, then that's, we can find that by just taking the limit of the leading term, and which would be either infinity or negative infinity. And whether it's positive or negative infinity, that's going to depend on the degree n and also on the coefficient an. When we are looking at the limit at infinity or at negative infinity of a function, we are basically looking at the end behavior of the function. That is, what is the behavior of the function as x gets bigger and bigger in the positive direction, and what is the behavior of the function as x gets bigger and bigger in the negative direction. In other words, we are asking what is the ultimate behavior of the function what is the ultimate behavior of the function in the positive direction, and what is the ultimate behavior of the function in the negative direction. So when we take the limits, when we take the limit when we take the limit at infinity, we are trying to describe the right end behavior of the function, and when we take the limit at negative infinity, then we are looking at the left end behavior of the function. So here's a polynomial. We want to know what is the limit of this polynomial as x goes to negative infinity. Well, like we said, the limit of this polynomial at negative infinity would be the same as the limit of the leading term at negative infinity. Well, what's the leading term here? Well, negative 4 times x to the 5. Now, when x is negative large, x to the 5 will also be negative large, but there is another negative here, so we get a positive large here. So that tells us that as x gets bigger and bigger in the negative direction, this leading term is getting bigger and bigger in the positive direction. So this limit would be positive infinity. Again, make sure that you understand that infinity is not a number. When we write that this limit is infinity, what we are saying is that as x gets bigger and bigger in the negative direction, or as x decreases without bound, this function is increasing without bound. So you can look at that in the graph. So the blue one is the graph of the leading term, and the red one is the graph of the polynomial p. So you can see that as x goes to infinity, the behavior of the polynomial and the behavior of the leading term would be the same. And similarly, the behavior of the polynomial and the leading term as x goes to negative infinity would be the same. So here is the limit. Here is the limit as x goes to infinity of p of x. While in that case, notice that when x is big and positive, x to the 5 is big and positive, but with the negative, it's a negative big. So this limit would be negative infinity. So p has the left hand behavior infinity and the right hand behavior negative infinity. So the function goes to negative infinity in the positive direction, and the function goes to positive infinity in the as x goes to as x increases as x. Okay, so in the negative x direction, the function goes to infinity. In the positive x direction, the function goes to negative infinity. Here is an exercise. So you want to look at the same. You want to look at the limit of this polynomial p at infinity and negative infinity, and draw a conclusion about the behavior, the end behavior of this polynomial. At this point, you should pause, try to answer this question on your own, and once you have answered the question, then come back to the video and see the rest of the video to see if your reasoning matches with my reasoning. Okay, so hopefully you have tried this on your own. So let's see. Now, the limit of p of x as x goes to infinity would be the limit of the leading term. So here, the coefficient is positive, and when x is big, x to the 7 would be big. So the limit would be positive infinity. When x goes to negative infinity, the limit here, when x is negative but big, x to the 7 would be negative and big. So 300 is positive, so we see that it's going to negative infinity. And so the right hand behavior of the function is that in the positive x direction, the polynomial is going to positive infinity. In the negative x direction, the polynomial is going to negative infinity. Here's how the graph of this function looks like. So the green one is the The green one is the graph of the leading term, and the red one is the graph of the polynomial. So you can see that they have the same, the leading term and the polynomial, they have the same end behavior. Okay, so I will stop the video here. In the next video, we will be looking at limits of rational functions at infinity.